Alrighty guys, good afternoon everybody from Australia and New Zealand. My name is Esfandiar Kuhi and I'm multi-product team leader here at In Central Innovation. And today we're starting the series of, let's say, webinars. And the first topic we are going to look at why SOLIDWORKS Simulation, how we can validate and optimize our design, and also we will have a look on return of investment. All right, first about the agenda. The first question we get is why we need simulation, how simulation is required, why simulation is required in our daily activity in design and design validation. In that regards, what we do, we're looking at the features of SOLIDWORKS simulation standard, and we will start with the case study of linear static study, how we can validate for specific factor of safety with our design when you're using linear static studies. Then we follow up our case study by, tracking the design change using trend tracker. So initial design being validated, now we are planning to introduce design changes, and we would like to track the change in terms of what are the factor of safety change and how the mass is being reduced and etc. After we doing that, the next question and the next feature we are covering is we estimating life and damage in fatigue study and basically predicting under the loads and stress values we predicted in our linear static studies how many cycles this load can be repeated and when there is a fatigue effect, either it could be a break or anything else in our design. And the last and very important session we will run is to look at return of investment. So how much you investing and in what sort of time frame we get our investment return back and how much improvement and benefits we got with SOLIDWORKS simulation. Alrighty. Now let's start with why simulation. If you have a look to the traditional procedure of design and validation, it is starting with creating any 3D CAD model, either a single part or an assembly, building the physical prototype, and after that, in practice, we test the performance. Any problem we identify in a test performance stage, all this procedure needs to be repeated. Means we have to go modify our design, rebuild or modify the physical prototype and test it again. And this serial loop is getting repeated more and more until we get the final result as it's desired. And obviously you can understand this can take a huge time because it's required a lot of different resources and obviously very costly since we need to rebuild all the actual parts and components. Now, if we're looking at simulation to come to this procedure is following up as you can see. Still you're creating a 3D CAD model and then you building the virtual prototype, not physical one, which is not a costly. It's basically your CAD model, maybe with some simplification on it. And then exactly what is happening in the reality as a loading condition, as a performance condition, and everything else can be simulated. And simply, we can do all this procedure without really building a physical prototype, which is costly, or require a variety of people to be involved to make this happen. Therefore, we can do the validation on the design in a very low cost, let's say, scheme. So if we have a look again, any traditional or typical serial procedure is starting with a project concept, either it's mechanical or electrical design, then after that is happening the design validation and technical communication, and then it's going to operation. But if we're taking SOLIDWORKS proposal, design stage, design validation stage, and communication stage are happening in parallel, not in a series, or let's say after each other. And this is exactly where you save time and money. So for obvious reason of making things low costly and happening all after each other, all together rather than after each other, we can say this is the way that we need to, let's say, utilize simulation tool in our design validation activities. All right, so with that justification, let's have a look to the solutions we have. In SOLIDWORKS FEA side, finite element or a structural analysis, we have three different levels of simulation. Simulation standard, simulation professional, and simulation premium. Basically, all of these tools are adding to your CAD software, whatever CAD level you have in SOLIDWORKS. If you have any of this license, it will be activated over that one, and you can perform variety of tasks as you can see here. And as we said before, we are going to focus on linear static study cases, fatigue cases, trend tracker, and obviously you can see there are motion study, which is rigid, let's say dynamic analysis, or let's say designing mechanism, which is not the focus for today's webinar. All right, let's have a look through this procedure. Before we going through more details of our case study, let's eliminate some ambiguities about finite element analysis, or let's say define it. We're starting with a very simple example here. Imagine from the doorstep to the mailbox, there is a pathway like that, and we would like to measure it with the yardstick, as you can see. So basically what you do is you starting from the first point, putting the yardstick and estimate all these pathway and curves with single straight line segments, as you can see. What is the disadvantage in this method is we are going to estimate all the curves with the straight lines. So this straight line is not exactly at the same size of the curves. So for let's say solution, what we can do, we can modify the yardstick to be smaller and smaller while our estimations are getting closer and closer. However, on the other side, what is happening? We are spending a lot of time to do this measurement. Well, if we're using bigger one, maybe with 2 or 3 measures, we can estimate the pathway lengths. So which one is better? Basically depends on how accurate we need the answer. So there is no yes or no answer to this question. So if you like, you can use a caliper to do this measurement, or you can use your walking pathways to say this is the pathway. Therefore, the question of how long is this pathway can be answered differently, depends on what sort of tool we're using. We have the same concept when we're doing simulation or doing FEA analysis. You have a CAD geometry and you need to represent it as an FEA model or finite element model using your, let's say, measuring stick, which called elements. Elements are basically a tetrahedra or triangles sitting in your model, and network of them, which is called mesh, is simply going to represent. Therefore, smaller triangle size, when it's going over the curves, can estimate it better. But what is happening? We have lots of them. All the calculations are happening at the nodes, where those elements are joining together. So more nodes we have, more time we have to spend to get them get the result. And again, is it the best one to get as much as we could? Depends on how accurate you need the answer. So finite element is basically working on a very simple concept of representing your CAD model, or let's say your geometry, with a network of elements called mesh. All the calculations are happening over the node. Having a closer look through the procedure, we can find we have a CAD geometry with all detailing, and now you can understand there are so many features such as cosmetic, let's say fillets here are represented. So if we want to represent that small fillet, we need to have a very small measuring, let's say stick or element size. Well, is it necessary? Is it cosmetic or functional? If it's functional, yes, we have to do. If not, then simply ignore it. That's why from your original design, you always need a simplified CAD geometry. Well, all unnecessary, not functional features are going out in order to save the time. From this point, you entering the FEA building model procedure. Well, you are answering a couple of questions such as type of analysis. Is it linear static? Is it fatigue? Is it any other one? Then, more importantly, what is this component made of? We obviously know that if you're building this material bracket from steel, the response to the loading would be absolutely different if it's made of, for example, rubber. So the response of the material to the loading is appearing as a material properties. And this is the second question we have to answer and specify into the software. Then, how our actual design is connected or related to the rest of the world. Support. What sort of working condition we have, pressure, force, let's say temperature, etc. So it's coming to loads. When you answer all of these questions, you prepared your FEA model, and we can see pre-processing stage is simply getting completed. From this point, we have to do the conversion, say this is my element size, and the software will do the mesh for you, run it, and then you have all the results in terms of stress, strain, displacement, factor of safety, and etc. And you can see and review your design if it's performing in the way that you like or there is a failure here. Okay, so we understood the whole procedure, how we build, how it's progressed. We will see a case study on that one. Now, more importantly, before I move to the case study, is to understand two main assumptions we make here, linear, static. And these two words got a lot of meaning in them. First, let's look at the linear. We call a material linear if the response of the material to the force is linear. For instance, you can see there is a linear line here. Okay, when you are applying 1 Newton and your model is displaced by 1 millimeter, then you apply 2 Newton, it would be 2 millimeter. So that's what we call linear response. Any nonlinear material will respond as a curve. You can see 1 Newton, 1 millimeter, 2 Newton, maybe 10 millimeter. So that's called nonlinear. Most of the, let's say, ductile materials, such as steel product, have a very significant linear region. And this linear region will remain until the actual material coming to a point which is not acting linearly anymore, and that's what we call yield. What is happening there? Then the deformations are going to be permanent. So in linear region, if you are putting the load, you get the deformation, and simply you're releasing the load, everything is going back to the original place. In nonlinear region, everything would be on permanent deformation. So the concept of linear is very important to understand. We have small displacement, original and final shape are very similar. Material is acting linearly, and also when we remove the load, there is no permanent damage or permanent deformation on the structure. The second terminology we can see here is about static analysis. Static means when the loads are applied slowly and gradually, and there is no time dependency. Imagine there is a chair, somebody is standing on it. This is a static load. Imagine if somebody is jumping on the same chair. This is not a static load because it's suddenly applied in a very short time frame. This is what we call dynamic. Therefore, the first question you always have to, let's say, answer is, what is my material? What sort of loading I have? If it's fitting to linear static, that's why you can choose the linear static in SolidWorks Simulation standard. So if the assumption is getting false from the beginning, for example, you have rubber rather than steel, then there is no linear here. If somebody is jumping, dropping the actual component or design, it is not static anymore. It is dynamic. So that is a very good, simple, let's say, a question we have to answer to start with the correct pathway. All right, with all this explanation, we're coming to the interesting point of looking at the rod. A connecting rod with the initial design, as you can see here. The working condition is pretty basic. You can see there is a ball bearing hinge connection on here, 2 fixing bolts, an active compressive load of 20,000 Newton. What we would like to do is first to do or perform linear static analysis to understand if this design is fail or not, what sort of stresses are, let's say, detected. Is there any deformation, and if it is, how much it is, and looking at the factor of safety. All right, let me bring the model. Here is my rod model. As you can see, it's a single component made with multiple features and ready to be analyzed. As we said, guys, we have the CAD package, and if you have the simulation, you go to the add-ins, activate or tick on your simulation tab, click OK, and here it is. Simulation tab is ready, and now you can do the new study creation. So again, what I'm repeating, simulation is not a standalone product. It is an add-in, and you need a base CAD software. So we can go to new study, and this is what you can see. Again, depends on your license type, you can have variety of studies. With SolidWorks Standard, we can get static and fatigue analysis. With the next level, more options are available. With the premium level, all options are available. So give it a name as we like, click OK, we build the case. Now I do have static tab as my design evaluation, and I have the design tab within the same file, and this is the main proposal of SolidWorks Simulation, design and validation at the same time. So there is no third party. Any changes you make in your model, you can see it is updated in your simulation as well. And that is a huge advantage we got here. Now looking at the new tree we got a study called static, and basically the procedure we have reviewed can be seen in this tree as well. We have a part with the name, right click, and you can apply material into it. Right now it's titanium. I would like to go see if it's carbon steel. Well, we're looking at the material properties, and what we can obviously see here, there are a variety of properties being listed with the value. Some of them are red. Elastic modulus, Poisson ratio, yield strengths. So you can see in any linear study, these are the values we have to know. Otherwise, we have missing point or missing inputs. So all the red values is what we have to have. Blue values, like thermal expansion coefficient. If you have a temperature load, you might need it. If you don't, there is no point to it. So that's why they are blue. We might need, and there are some black ones, such as specific heat. In any linear static studies, we don't really need to know specific heats. Okay, now after correct selection of material and reviewing material property, which is very important to have, you click on apply, close. You can see your material is being applied, as you can see it in a bracket, and there is a green tick. So the first question of what type of analysis been answered, linear static. Second, what is the material? Yes, carbon steel here. Obviously, what we can see here is the connections, means we need to have multi-bodies or assemblies or multi-parts to have the connection defined. So you can see there would be either the definition of the contacts, or maybe they are just getting connected with the springs, pins, bolts, bearing, and etc. There are heaps of options we can have. And again, it's not our main concern today, since we have one single component, none of them has any meaning. Now going to the next step, and we can see fixtures, means how our actual design is connected to the rest of the world. Right click again this option, we can see a variety of selection we have. Either it's a fixed geometry, roller slider, fixed hinge, elastic support, bearing fixture, foundation bolt, or even advanced fixture. Let me pick up fixed geometry. You can see by selecting any of these options, there is an animated GIF, which is showing you what does it mean. You have the option to select any face, any point, or any edge to be fixed. Simple as I go here, select this one and this one to be fixed. I've done my job. And it's showing you what is happening. The selection will be fixed forever, and there is no force in the world which can remove or displace it. So clicking OK, you have defined your fixture. You have more fixture. Let's go ahead and add another fixture. As we said, I would like to add an let's say fixed hinge here. You can see the fixed hinge is providing this action. And simply I'm clicking on the cylindrical face. Let's have a quick look about advanced options we have. In advanced option, you have a variety of, let's say, selection to define your fixture on flat faces or even cylindrical faces, and restrict one or all degrees of freedom, axial, circumferential, and radial at the same time, or individually. So cylindrical faces, also we're talking about let's say spherical faces, flat faces, either symmetrical, let's say conditions, or what you can see in your advanced selection. But let's stick to our problem definition. I've got the face to fix and simply clicking OK. So fixed hinge is what I want and simply OK. Now I can see I have two fixtures here, fixed, fixed hinge. All right, that's how my actual design or component is connected to the rest of the world. Now from this point, the next stage is what are the external loads. Again, we have a variety of options: force, torque, pressure, gravity, centrifugal forces, temperature, and etc. You can see all of these options here. Let's pick up the force. And again, what you can see, there is a selection box to say apply force on a node, on a line, or a face. So I'm simply clicking on this one. What you can see right now, the force is getting applied normal to my selection. What we would like to do is to make it directional. That's why I'm selecting the second option, select direction. For referencing my direction, I'm using any existing plane, including the main ones, such as this one. And now you can see there are three components of force. I can make them active. 1, 2, and 3. Normal and shear forces at the same time. Simply we can get the face to apply load, refer it to a plane for direction, and putting the magnitude. So for that reason, we got 20,000 Newton to be applied. Right now it's look like tensile. What I would like to do is to make it as compressive load. All right, clicking OK. I have fully defined my mathematical model, or let's say pre-processing stage is finalized. Material ticked, fixture ticked, loads are complete. Now it's the time to convert our CAD geometry to network of elements. Right click, create mesh. As we said, your measuring stick or element size could be very big, as you have coarse mesh, or it could be very, let's say, precise, as a fine mesh. But this is very, it's not very clear what does it mean, how coarse, how fine. For that reason, there is a mesh parameters here. And what you can see, it's element size as global scheme here. And if you make it fine, it is 1.9. And if you make it coarse, it is 7.6. The very interesting thing about SOLIDWORKS simulation, as I said, is fully synchronized with the CAD, means all geometrical information is there. This suggestion as something as a mid-range is coming automatically based on the dimensions you have in your model. So it's a very smart suggestion. It's not coming from middle of nowhere. Since all the geometry IDs are stored in this file, you can see this suggestion is smart enough. The other thing we can see here, the mesh parameters could be, let's say, the different scheme you can do. Standard mesh, same size element everywhere. Curvature-based mesh, interestingly, can have variety of element size. So when it's going to a tiny features, it can adjust itself to 1.2, and when it's coming to the bigger faces and flat faces, it could adjust to 3.8. Again, that is telling us the meshing is happening here is pretty smart and to the point. It is optimized. It's not generating more unnecessary result to waste the time or less that you just simply compromising your accuracy. So if you click OK, the meshing procedure start and you have the converted model geometry to mesh. Now this is the time we go for run this study and looking at the result. Here it is. You can see there are 3 plots being generated automatically, and the first one is von Mises stress as one thing we can see. Any of those plots can be modified to show variety of different components such as normal stress, shear stress, and etc. As you can see, units can be changed. Yes, go to megapascal. Also, you have the option to look at the stress on variety of isolated faces. For example, I would like to have here and here to be shown. Here it is. I can do the isolation here. Or if I don't, I would like to see the whole thing. Here I am. You can see automatically I've get the deformed shape displayed. In a chart option, you can ask for minimum, maximum to be pointed out for you. In a legend, what we can see as a result, yield strength is 287 megapascal. Right now, we have 145 megapascal. Means there is no yield. That's good. Our model is not failing. However, this is maximum and minimum calculated. I would like to change my legend to filter the stresses up to 90 megapascal. I can do that. Well, any region with the red color, we have 90 megapascal at least, and it could go above. So you have the option to specify the region with some specific, let's say, values of stress. Also, scientific or general, there is no problem. Here it is. Make it more readable, and you can see, yes, the maximum stress we got is around 146 megapascal. Below the yield, everything is fantastic and fine here. So I'm happy with my results, and this is my stress result. Second result I can see, displacement. I can see how much displacement happened. 4.6 E2, the maximum displacement happened at that area. And I can definitely animate it and understand the characteristic of it. Lower speed frame and save it as AVI if you like. Now the next question is that all I can see here? Can I let's say generate more figures here? Yes, you can do. Right click on results and you can see variety of let's say plots we have here. Define another stress plots, any let's say factor of safety, and etc. Let's pick up factor of safety for all the bodies existing here. Click OK, and what we can see, most of the regions are coming with the factor of safety of 1.9, and there are some areas which is exceeding and have infinite let's say, safety on them. So perfect. I've got all I want. Stresses are showing me good. Factor of safety is around 2. Everything clicks OK and very fine. Now I have my next question. And in my next question, what I would like to introduce is simply, I would like to, let's say, introduce design changes. And I would like to track them. For instance, I'm happy with what I got initially, but what if I make the thickness decreased? Can I introduce a cut here? Or if I introduce a cut, then later on, can I add a support? What are the stress? What are the factor of safety? How much mass I'm saving going over these scenarios? Should I create multiple studies and compare it manually? Or there is, let's say, a mechanism here which I can do the trace? Okay, the answer is yes, you can do. We have a feature in SOLIDWORKS Simulation standard, and we call it Trend Tracker. Here it is. In your current study, all the results are fine. Let's save them. And then I would like to create a trend tracker. As long as you click, you will see that trend tracker with the trend journal to record all of the changes. Now, we would like to start from a point. What we have done, or let's say our initial design, is the starting point. Therefore, I have to right-click, say this is the baseline. Yes, as you can see, all of the result is being recorded as a baseline. And interestingly, if you look at your trend tracker, now you have 3 properties to be traced. For example, look at the mass. Right now, how much it is, we can see 272. Now, if you ask the question, all right, there is a mass, stress, and displacement. What about factor of safety? I would like to add another trend tracker parameter here. Yes, you can do it. For any parameter needs to be traced later on, we need to have a sensor. Well, you can obviously see there is a sensor here. Adding a new sensor. It is a simulation sensor. It's not a stress, strain, displacement, or anything else. It is factor of safety. You can see there is a big list, depends on your study type. And we would like to see at least the model minimum. Click OK, and now we recall it here. Add a trend tracker data graph. Mass, stress, displacement are there. I'm selecting minimum factor of safety, clicking here, and I've got 4 of trend tracker graph. Right now, this is what I have as a factor of safety. Now it's the time to introduce our design changes, and we are make sure all the parameters which is important for us to trace them are set up. Okay, I'm going to double click on my design. All dimensions are shown. I'm selecting 16 and I'm changing it to 14 millimeter as our new change. I'm running this study, going ahead and solve, clicking yes. New results is being generated. You can see my stress is now 167, have a bit of change. My displacement have a bit of change. And I would like to compare. That's easy. I go here, stress, and 146. Now it is 167. That's how my stress is being changed. Still within the range. That's good. So even if I make this rod, there is no failure based on the stress report. But interestingly, how much mass I save? From 260 gram, I went down to 226. Some mass change. So initial thinking was not perfect one. I can see still with the same design, but reduce the thickness, I can get some satisfactory results. And obviously you can look at the factor of safety from where it was on iteration 1 to where it is in iteration 2, 1.7 compared to 1.95. All right, so look like I made one step forward. And imagine that much of mass saving in a high volume production, how much saving it is. With simple question we ask, executed in a couple of seconds, we found a huge saving here. And if in practice, in a real practice, you want to build this model and test both of them, you can now imagine how much money you have to spend. Let's do the next change. I'm going to my model. There is a sketch here. What I would like to do is make a cut extrude, which is happening through all, in both directions. Alrighty, so I've made it even lighter here in this version. Rerun the study. That would be my second attempt. And when doing so, and now I can see the new result. Interestingly, I can see there is some failure here. So the actual stress is 311, which is exceed, and it is not showing me the correct thing. So looking at the stress, that is how it went up. If I'm looking at my minimum factor of safety, right now it's coming less than 1. So that move was not a perfect move here. Therefore, what I would like to see with a little bit of support in the cutting area, what would be the new trend? I go back to this one, select my sketch again, and this time I'm adding a bit of material to it. So 4 millimeter of support, going through mid-plane, adding on the same direction, and simply this is my last design change. I brought it here, rerun the study, and obviously get the result. Much better now. 189 less than what we want, and let's look at again the journal we have. Stress significantly drop. Look at the mass. Here it is. From something which was failing with the total mass of 150, we just added like 20 grams. And simply our stress is significantly changed. Look at our initial estimation, 260. Look at our final mass. We got 171. Huge percentage of mass saving. Stresses are perfect. Factor of safety from 2, just we compromise a bit, 1.5, which still can be acceptable. Now we can, let's say, clearly understand if all of these 4 design changes needs to be executed in a reality, how much time we spend, how much money we spend, and how much, let's say, effort required. With these simple clicks, we can trace all of them. And the good thing here, you have your trend journal. You can click on it, it will publish all of your attempts with the results as a series of tables. Or alternatively, if you need any of your results, you can go to the gallery and look at what you got one by one in a different case studies. Either a stress, either displacement, and etc. So your gallery has been recorded with all the attempts, your chart's been recorded with all attempts, and you obviously can go and generate your report, which is again another automatic scale, let's say, procedure here. So all the data is getting, let's say, generated, and we will go ahead. All right, so very easy. We found the response of the structure with linear static. With trend tracker, we find the best design and we trace the changes. Now we are pretty confident with what we got as a design. We finalize it. The next question is, all right, for an instant of load, which is one static 20,000 Newton load, there is no failure, and I'm pretty happy with the weight, with the stress, with factor of safety, and etc. Now, what's happening if this load is getting repeated? So we would like to provide warranty for our design. using fatigue study. So the final design is going to be on a fatigue testing. And what we would like to say in a fatigue, if my loading or the mean stress is going to be cyclically repeated million times and getting fully reversed, plus 20,000 Newton minus 20,000 Newton. And this is going to happen for not one time, 1 million cycle. And I would like to see what are the damage and life result. Is there any failure there? Because every single design will have, let's say, a repetitive load on them. So for that reason, what I need to do, I have to simply move on to my last type of study, which is the fatigue study. In any fatigue study, you have the variety of saying, I have a constant amplitude, like on and off, or fully reverse, or even your load could be a variable amplitude. There is no trend on them, like crazily and let's say fluctuative sort of loading here. So clicking on this one, constant amplitude, what you can see, there is a new study like fatigue. What we can see, asking first, what sort of loading we have. So right click, be adding an event here. So we have a static study here, which we recall it, and saying with the scale of 1, all the loads there going to repeat it for 1,000, which I'm putting 1,000,000, and it's getting fully reversed. You have more option to say 0 base or with the ratio or cycle picks. Clicking OK. That's the first thing we done. Now, it's more than important to always remember, for fatigue studies, if I bring my, let's say, slide back here, there is a relation between how much stress can a component can tolerate depends on the number of cycles. Highest stress can be tolerated for 1 cycle, and if you're repeating, the number of tolerating stress, the value of tolerating stress is reducing. And that's why fatigue is starting. So this is called SN curve. And this is something definitely you have to present and tell the software what is the relation between the maximum stress tolerable to number of cycle load is being repeated. For that reason, again, we can see the part name, apply fatigue data. For the carbon steel, you can see if there is any table and curve, you can see them. If not, you have the option to say, for that cycle, this is the stress. And you simply add or type, bring it from any file, and a very common and very accurate approach is to use investme codes to generate SN curve, usually for austenitic steels or for carbon steels. There is one standard material with the curve, and the other similar material having the same curve with the same slope and everything else, but depends on the elastic module. This is going to be changed. This is a very good approach, at least initial approach, if you don't have the SN curve here. So simply we use that one, click apply, close. We told software 2 main information. What is the SN curve for this specific material, relation between stress and life cycle, and what sort of stresses from which study is getting repeated how many times in what sort of fashion. The rest is simply running the analysis. Look at the life. For 1 million cycle, anywhere with the red, we are happy. For the other region, which the minimum is 2.7 E4, is the minimum life we get in our design. It looks like what I've designed here, tested from initial point to the last stage, is all ticking the correct box for me. Initially what I was thinking, how progressively I've modified to get minimize the mass and having the at least 1.5 factor of safety, and even for let's say 2.7 E4 cycles, it won't fail. Again, you have the option to, let's say, get back, add more trend tracker study, and make sure you're meeting the total life as you want, the best configuration as you need it. Alrighty, guys. So this is a complete procedure. We made it quite simple with one simple part, but the capabilities of SolidWorks simulation is not limited to that one. Complex assemblies with lots of connectors, contacts, and etc. is definitely here, and there are heaps of let's say examples that are let's say everyday big brands are using to perform and do the evaluation. But the main idea for SolidWorks simulation is to understand and do the validation before you're making anything in a physical fashion. All right, now for the last bit of this talk, what I would like to show you is the ability that InterCAD and Central Innovation to present or analyze your return of investment with SolidWorks simulation. What I will do, show you a sample of a case study which we done, and we let's say present the data, how much saving and in what sort of time frame you will get. All right, let me bring my profile here, and here it is. This is a tool which is accessible just by us, and if anybody requires to raise their capex and they need our assistance, definitely I'm more than happy to keep in touch, put the customers let's say input into it, and let's say send you the report on it. But let's have a look what we have here. So obviously you can see the name of organization which I put ourselves here. Business in Australia, we can see there are lots of other regions in all around the world. And obviously organization business here as an industry, you can see a variety of businesses, and simply from this point we putting the important information. The first question was the team size, 2 people with the average salary of $75,000, and we anticipating the growth in a project or design or development in a team size in next 2 years, not immediate, next 2 years of 10%. And also the other question, which is very important, is number of design or development project over the next 12 months is like 5 projects. Anticipated growth in a number of projects per year, again starting after 2 years, is 10%. The current situation, if you're using in-house simulation, means you have the simulation and you're thinking about upgrading your simulation tool, or you outsource it, or let's say absolutely no simulation at the current time. You can see there are more information required, some such as number of engineering changes before SolidWorks simulation. I'll put even 0 to make the case as a worst case scenario, even you are not having any issue with that one. Let's say annual cost of a scrap is like 0, but I've put instead the percentage of 10. Number of new product expected to be developed and launched in next 12 months is just 2, and very, very low figures here as an average first year revenue expected for each new product launch is just even $1,000, which is not existent. But I made it on purpose to make the minimum, let's say, requirements and cost in the current operation. So we put in the, let's say, profile. Now let's move to the benefits. What is happening? The analysis is showing us the annual saving of $174,000 and the total saving over the 3 years of $500,000. Reduce current cost is 0, improve efficiency like 63, and improve effectiveness is 111. And do not forget, reduce cost is 0 because we said there is no scrap at all. If we're adding to that equation, that would be a very significant figure. All right, so you can see more into the details of each category, like reduce the cost, like improve the efficiency, like improve the effectiveness with software, with SolidWorks simulation, and also we can see the total at the end. More importantly, all of this can be shown as a different graph. And in ROI analysis tab, what I can generate and I will modify is the cost for you to have the SOLIDWORKS simulation here. Well, what you can see here, for the licensing, initially you're spending, for example, 18,000. Doesn't mean the software is costing that much all the time. For the first year, second year, and third year, you won't pay anything for the software. Obviously, you have the subscription services, which is constant over the years. And we can see there is a training cost, which is $3,000 initially for 2 people. And this is how much you spend on the first year, on the second year, third year, and etc. All right. So what we can see at the end, with including all of these costs, are simply 84,171, 267. And obviously you can see we're meeting less than around 5 months. You will get your return based on your purchase and investment. And after that, it is all benefit for you. There are heaps of case studies if you like. For instance, if you like, I can send you the links and you can read Driving a Better Design with SOLIDWORKS Simulation, and you can see the case studies here. Also, what else we have? You can go to Report. And on Report, what I can see, I can generate you a report and send it to you as a Word document. So create a report and open it. This is something you can submit to your board of manager to look at all the steps and all the figures with the summary and figures, as you can see here. And obviously what we can see, it's very important. Payback period, 5 months. Just in 5 months with very low numbers I've got here. All right, and summary of it. The other format I can provide for you is the presentation. Either if you have to present it to the board of management, the PowerPoint presentation file can be ready and again sent to you very shortly. So what we can see here is such this report. With PowerPoint has been ready, total benefit, total cost, obviously modifiable by you, and simply present it. So guys, we come to the conclusion. What we have reviewed in our session. First, we understood why we need simulation tool, how it's going to help us, and why it's going to be very important to have it. We reviewed one specific product, SOLIDWORKS Simulation Standard. And we said what are the linear static studies requirements. We trace the design changes with Trend Tracker. And also importantly, as one of the essential steps for the validation procedure, we went to fatigue study and understood life and damage over 1 million cycle. And obviously on top of that, if the raising of question how much I have spent and when I'm getting the return, we obviously get the figures shown to you. Now from this point, if anybody have further technical or commercial, let's say, question, please contact me directly, Svandiar Kuhi at intercad.com.au. And be definitely more than happy to provide more specific information as it's required, looking at your case study, going more into the figures, looking at a variety of options with the software, and obviously at the end, if you need ROI analysis specifically for your company, we can do it and send it to you. I would like to thank everybody for your time and attendance. We are going to have more webinars from tomorrow and the next week also. Please make sure you're attending to those one if it's in your area of interest. Thank you so much. See you next time.